Hello and welcome to this episode of the Cyclo Edition, the podcast for those looking to go above and beyond in their understanding of the organic literature. I'm Matt Genzink, and I'm joined today by Grace Lutovsky, Wesley Swords, and Yuki Lee. The paper we'll be discussing today is titled Arylation of Axially Chiral Phosphorothioate Salts via Dinuclear Palladium Catalysis, and it's from the group of Franziska Schoenebeck, who is a full professor at the Institute of Organic Chemistry at RWTH Aachen University. Her group focuses on understanding and predicting chemical reactivity through computational and experimental means. The paper we're discussing today reports the first direct carbon-sulfur coupling to make S-Aryl phosphorothioates.
So looking at this paper, they are trying to derivatize these phosphorothioate salts. So looking at what a phosphorothioate ester is just a phosphate ester that has one non-bridging oxygen replaced by a sulfur atom. So this group is really significant because they've been used as axial chiral catalysts. They're also very relevant in medicinal and agrochemistry.
Right, and so I was reading through and I found a couple of interesting reviews just on these styles of chemistry. And so the way that these phosphorothioates are used in medicinal chemistry in particular, as well as some of the agrochemically, is as antisense oligonucleotides. And so those are just oligonucleotides that have been derivatized and changed from your kind of standard phosphate backbone to now have phosphates either with sulfurs or amides or those sorts of functionalities. And it helps basically just broaden the range of activity of these functionalities, as well as make them more resistant to being chewed up in the body and better drugs. And so there was a review in 1996 that just mentioned that phosphorothioates have long-term potential, but there may be some sort of unidentified flaw that they'll have to overcome, and that there needed to be more investigation and optimized. And so the same author on this, Bennett, wrote a 2017 review that now detailed, again, the massive growth of oligonucleotides in those just 20 years. And there are now these sorts of phosphorothioates, as well as other oligonucleotides that are just span kind of the realm of disease. And so that review then ends that there still needs to be further improvement of these drugs, and one of the key ones that they point out is the development of novel chemistries as well as formulations. And so that's really kind of what this paper does, is provide a method to derivatize phosphorothioates.
So antisense therapy is a form of treatment for genetic disorders or infections, and in general what it is just synthesizing a strand of nucleic acid. So whether that be DNA or RNA or something similar to that can bind to the messenger RNA and basically inactivate it. So these are oftentimes used to combat genetic disorders, and basically you're just inactivating that gene.
Yeah, either inactivating, or in some cases, if you steroidally hinder the ribosome from binding it, it also hindered the translation. Or there's something called splicing, which is basically when you have the introns and exons, which are the parts that the mRNA either translate into protein or become silenced, then having that antisense oligonucleotide can alter the splicing so that we kind of control the proteins that gets expressed.
Yeah, and this is why you can't just use a complementary DNA strand or an RNA strand, though, right? If you just were to take and make your typical phosphate backbone strand, it would be chewed up by nucleases in the cells. So these phosphorothioates or other antisense oligonucleotides typically have derivatized backbones or changed backbones. In this case, it's switching out one of the oxygens for a sulfur, and that just really allows the oligonucleotide to live in the body up to days in some cases. And so these things can be dosed over days rather than having to take multiple times a day.
Right, and one main challenge of these antisense oligonucleotide therapy is that the drugs are usually not very good at crossing the blood-brain barrier. So they're usually given as injections directly into the spine or the fluid around the spine so that they can take effect in the central nervous system. And what's more, a lot of these drugs are given multiple doses. So just imagine having to do those injections over several times.
So one common example of a drug that has this phosphorothioate ester linkage in it is Spinraza, which is actually the first treatment for spinal muscular atrophy that just came out on the market in 2016. So spinal muscular atrophy is a disease that affects the motor nerve cells in the spinal cord, which eventually weakens your ability to speak and move and even breathing. So it's not a great disease. It is the most common genetic cause of infant mortality. And I also read that it is estimated that 1 in 50 humans actually carry the gene for this disease.
So the structure of Spinraza is 18 nucleosides bound by these phosphorothioate linkages. And the structure is very complex, very hard to make, which is kind of shown by the fact that each injection, each dose of this drug costs $125,000. And these phosphorothioate linkages basically introduce stereochemistry because for these linkages, each phosphorus atom is a stereocenter, which results in 17 different stereocenters in this drug, whereas regular phosphodiester linkages don't have stereochemistry. These phosphorothioate linkages do. So 17 stereocenters. If you calculate how many distinct stereoisomers this molecule actually contains, it's 2 to the n, so 2 to the 17th, and that's more than 100,000 distinct stereoisomers.
Currently, this drug is sold as the mixture of all of these stereoisomers. Because this is so complex and the methods to define each chiral center is so complex and there weren't very many transformations out there to do this, makes it so they have to really sell the mixture of diastereomers, but yet we can only assume that more than likely not all of them are the active drug.
Right, and I mean a lot of the information that we're using here is coming from a Phil Barron paper in Science that came out in 2018 where he developed a novel methodology to synthesize these phosphorothioesters in an enantioselective method using basically a chiral auxiliary scheme to make a chiral phosphorus center and then displacing that auxiliary as well as a sulfur substrate, which then ended up giving you your phosphorothioester complex. He was able to apply it to the synthesis of nucleotide dimers as well as apply it to enantiopure polynucleotide.
So this Barron paper developed a method to control the chirality at the phosphorus center, and he showed many different derivatives and different applications of this in his paper. All of these applications all have a phosphorus sulfur to hydrogen bond in them. So the sulfur here is not derivatized, but there is a potential for derivatization of these molecules at that sulfur atom. And this is really big because one of the main themes in medicinal chemistry these days is all about late stage diversification. And so this sulfur atom could be a access point to further derivatize these molecules and potentially come up with other drugs or other applications for these molecules. And so that's what this paper highlights today, is the derivatization at this sulfur atom.
In thinking about derivatizing these phosphorothioates, one can imagine two different disconnections that you could make around the phosphorus to do this style of chemistry. Either you could break the phosphorus-sulfur bond, which would basically lead you to a reaction between a sulfide and a halophosphate. So you'd have to do a coupling reaction between those two reagents, or you could imagine breaking the bond between the sulfur and the carbon and doing the reaction between a thiophosphate anion and just like an aryl halide or an alkyl halide or something like that. And so Francisca starts by stating that there are methods to do the phosphorus-sulfur coupling reaction, and one of the ones that I looked up was a Michaelis-Arbuzov type reaction in which you can take either alkyl sulfurs or sulfur halides or thionyl chlorides and react them with phosphorus reagents to give you the phosphorus-sulfur bond, which would in general lead you to this derivatized phosphorothioate, but limits you in the terms of your selectivity because you'd have to do that bond forming step between the phosphorus and sulfur enantioselectively. When we think about making that sulfur-carbon bond, you now don't have any role of the phosphorus center in that reaction, and so the chirality around that phosphorus atom should not be changed based on that sulfur reaction. The few reactions that have looked at doing that style of coupling don't start with the actual thiophosphate anion. They instead formed that in situ through reaction with elemental sulfur. And then the second step of that reaction is to then react it with some sort of alkyl halogen or some other sort of radical source through like a Chen-Lam style coupling. And so in that reaction, one, you don't start with like a chiral phosphorus center anyway. And then two, you're going through a radical Chen-Lam reaction, which going through a radical mechanism might be thought to ablate the stereochemistry that you would have around that phosphorus center.
So when the authors first thought about coupling at the sulfur-carbon disconnection, they thought that palladium-0, palladium-2 catalyzed cross-coupling would be a nice approach here because that system generally has high functional group tolerance. And in that regime, you can kind of imagine coupling an aryl halide. So basically, an aryl halide in the presence of palladium-0 undergoes an oxidative addition. And then they envisioned an iodide phosphorothioate exchange, basically to set up the reductive elimination that would yield the product. But in this case, they tried that with a couple of different palladium catalysts, and in all cases got no yield. The other experiment that they did to show that this wasn't a viable pathway was they started with the oxidative addition product. So they had a stoichiometric amount of that palladium catalyst in the presence of the phosphorothioate salt, and that also didn't give any product.
What that really suggested, and then they investigated this through density functional theory calculations, was that it wasn't the oxidative addition step that would be the problem for this reaction, but that either the transmetallation or the reductive elimination would be causing the problems. And so this group is well known for being both experimentalists and computationalists. And so they investigated the mechanisms for both of the palladium-0 and palladium-2 catalysts, and were able to show through this computation that the reductive elimination step was uphill by like over 28 kcals per mole. And so that large barrier to reductive elimination would slow down or just prevent this reaction from going forward. And so it was the reductive elimination from palladium-2 that was causing the problems.
So with these studies with the palladium-0, palladium-2 catalytic cycle, the authors kind of identified that the palladium-2 intermediate that's formed from the oxidative addition is potentially poisonous, basically meaning that the energetic barrier from that intermediate to the corresponding reductive elimination to yield product is too high in energy, which is kind of what Wes was saying. So they've done a lot of work with these dinuclear palladium-1 dimer catalysts, and they identified that system as something that could potentially work here. Normally when we think of these palladium-1 dimers, we think of them as just precursors to active catalysts, but they've shown that there are some systems where these dimers can actually be used as the catalysts themselves. So in this case, they start with a bridging iodide palladium dimer catalyst, and this catalytic cycle kind of has a reversal of the elementary steps as compared to the conventional palladium catalysis. In this case, the iodide phosphorothioate exchange, or what they call transmetallation, happens first, followed by an oxidative addition of an aryl iodide, and then the reductive elimination is last, yielding product.
Yeah, and I was reading on a review by Christopher Ueda's group this year on metal dimer catalysis, and one thing that they talked about is that when you have a less electron rich partner, then the reductive elimination is hard to occur. So this dimer catalysis take advantage of coupling this reductive elimination with the formation of a stabilizing metal-metal bond. So as a result, each metal has to only contribute 1 electron instead of 2 electrons, making this process more favorable.
Right, and their computations, again, support that this is what they're doing. So they, again, ran computations on this mechanism and compared them with the palladium-2, palladium-0 catalysis that they studied earlier, and showed that the oxidative addition is still pretty has a pretty high barrier, but once you've done the oxidative addition, the reductive elimination actually only has a barrier of 13-ish kcals per mole. So you've significantly decreased that step, and as the rate limiting step for this reaction, that helps really facilitate this reaction going forward.
The other somewhat interesting thing to note here is that the authors have already shown that they're able to do a trifluoromethylthiolation of aryl bromides. So basically, they've already shown that this dimer catalyst works with other carbon-sulfur couplings. So that may have given them some indication that it would be something good to try here. They've kind of laid out before that when you're kind of considering if a system would be good for this palladium dimer system, there are really two criteria that you should look for. One is if the nucleophile, so the nucleophile in this case is the phosphorothiolate salt, is able to replace a bridging iodide. And then the second criteria is that the nucleophile is able to stabilize the resulting dinucleum palladium framework. So they probed experimentally whether this system would meet the two requirements by taking the palladium dimer and putting it in the same flask with the phosphorothioate salt and basically monitoring it with phosphorus NMR. What they were looking for the phosphorothioate to basically replace that bridging iodide and then stabilize the resulting catalyst. And that's exactly what they saw. They saw a new signal at a different chemical shift, giving really nice evidence that this could function as a catalyst. Yeah, getting into the actual scope, basically they're just taking these aryl iodides and they're coupling them with phosphorothioate salts. So the actual salt is a tetramethylammonium phosphorothioate. And to start, they basically just are kind of changing the substituents around the aryl iodide. So they show a number of different examples for perturbations that they can make around the aryl iodine. They show that ortho substituted, meta substituted, para substituted aryl iodides all work in high yields. They also show a few examples of electron withdrawing groups, and they show a methoxy group as an electron donating group. So there's a decent scope here.
So when they were doing the Aryl scope, they used the aryl phosphoroesters, but they can also use alkyl substituents. And so they show multiple substrates with various alkyl groups off of the phosphoroester. And they also show that if these alkyl groups are chiral, they will stay chiral throughout this transformation. These products look more like agrochemical products.
For me, one of the key parts of this table and of the substrate scope were these alkyl phosphorothioesters. And that was because they really mimic agrochemicals that have been using the style of phosphorothioester functionality. They look similar to actively available agrochemicals that are used from pesticides, and the idea that you can do this in either with an pure ester groups, as well as vary that aryl group off of your sulfur is promising in terms of screening and accessing new libraries of these chemicals.
The second part of this scope is similar to the first in that you are coupling aryl iodides, but in this case, the phosphorus reagent is a Catal-derived organophosphorus compound.
Right, so Catals are usually prepared from acetals or ketals of tartrate esters, reacting those with Grignard reagents. They're very versatile in a lot of NA2 transformation because they are chiral hydrogen bond donors. At first, they were used for nucleophilic addition into aldehydes, obtaining good selectivities, and then there were also photoreactions that utilized Catal, such as 2+ photocycle additions and Nash type 2 reactions. In this case, with the phosphors, they're now able to act as ligands onto metals such as iridium, titanium, and rhodium.
One of the big draws for using Catal, say over vinyl scaffolds, is their ease of synthesis and the fact that you can start with either natural products or an anti-pure product relatively easily to give you these axial chiral ligands. And so the ability to do this coupling reaction on a Catal-derived phosphate is pretty reasonable, because all you can just go through now and screen a few different styles of arenes when you're trying to optimize your catalytic system.
So overall, this paper shows a great method to derivatize these phosphorothioate esters by forming that sulfur carbon bond. So how we can think about going forward with this now, and what we're really excited to see, is if they can apply this to scaffolds like Spinraza, where they have that sulfur hydrogen bond that could now be functionalized further. Can you do this sort of reaction and apply it and derivatize these other drug-like scaffolds?
And I think the real question here is whether this chemistry, or even possibly future chemistry in the group, would be compatible with the nucleobases that you're seeing on Spinraza and these other oligonucleotides. A lot of times these nucleobases have free amines, complex nitrogen heterocycles that may not necessarily be compatible with the palladium catalysts.
Right. And so towards that application, this method in particular may not be 100% effective, but the development of similar methods or potentially different ligands for their dimer may allow them to access those complexes. But the ability already to be able to derive things that look like agrochemicals and things that look like chiral catalysts and those sorts of things will allow this method to be very useful going forward.
And overall, I really liked the idea, I guess, and the vision for this paper, especially coming off of the Barron precedent from 2018. And I guess the whole idea is there's now a really nice method to make these chiral phosphorothioates, but it would be really nice, right, if we could derivatize them. So the idea is great, and I think the sulfur carbon disconnection is kind of interesting and not necessarily obvious.
Well, yeah, I think she mentioned this, and we did find a few examples where they do the carbon-sulfur disconnect, but a lot of the previous methods do the phosphorus-sulfur disconnect. And so by highlighting this method on a pretty big platform, maybe other chemists will now look at these molecules and see what other chemistries could do this same disconnect.
And that's our show. Thanks for tuning in to this episode of the Cyclo Edition. For more information on the paper discussed, we have included a selection of resources we used in our research at the end of the YouTube video. This was our take on a very interesting paper, and we'd love to continue the conversation with you. Please connect below the YouTube video and reach out on social media. You can follow the Cyclo Edition on Twitter and Instagram, where we will post regular updates about our next episode. You can also find the Cyclo Edition wherever you listen to podcasts and on YouTube. If you enjoyed this episode, please like and subscribe. We release episodes every other week, and our next episode will be released July 22nd. We'll provide the paper we'll be discussing during the next episode in the description of this podcast, as well as on social media a few days before the next episode is released. We hope you will tune in on July 22nd for our next episode.